Okay, welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we are joined by Mark Marley, who's come across to us from NASA Ames Research Centre. Mark did his BS at Caltech and a PhD on the oscillations of giant planets at University of Arizona. And then he came to Ames on the first occasion for a postdoc where he was studying the albedos of the icy giant planets of Uranus and Neptune. Mark then spent some time at New Mexico State University on the staff before he came back to Ames in 2000 as a research scientist. And since then he's been looking extensively at exoplanets and atmospheres of exoplanets. That's what he's going to talk to us today about the possibility of precipitation on exoplanets. So if you'll join me in welcoming Mark Marley.
Thanks, Avery. Thanks. It's been about 15 years since the discovery in the mid-90s of the first confirmed extrasolar giant planet and the first brown dwarf. Since that time, the studies of brown dwarfs and the discoveries of brown dwarfs and exoplanets have both mushroomed into major scientific fields. An interesting thing about both these classes of objects, the exoplanets and brown dwarfs, is that we've learned in the last decade and a half that to really understand what these objects are like, to understand their evolution, their spectra, their colors, you have to understand the role of clouds and hazes in their atmospheres. If you think about solar system planets, that's not really a surprise, because all of the solar system planets that have an atmosphere have condensates in the atmosphere that are important for understanding their spectra. Here is a slide I like from the Cassini mission that's combined a mid-infrared 5-micron image of Saturn, glowing red as it emits its internal energy and energies it has absorbed from the sun, combined with a scattered light image of light scattering off the sunlit hemisphere of the planet and scattering off the clouds and hazes in the atmosphere. You can see, when you look at the thermal emission from Saturn, that it's not just a homogeneous red glowing ball, but instead the light emerging from the planet is modulated by these dark patches all over the planet, which are clouds lying deep in the troposphere. Clouds have high opacity, and in regions where the clouds are relatively thin is where the infrared flux comes out. This slide really encapsulates everything I'm going to be talking about today as we attempt to understand what's going on in the brown dwarfs and in the extrasolar giant planets. And of course, this work wouldn't be possible without many of the collaborators that have worked with us over the years, particularly Richard Friedman here, who's sitting up front and has done amazing work on helping us understand the gaseous opacities of these atmospheres. So today, I'll say a little bit about the bestiary of objects that we have for both brown dwarfs and extrasolar giant planets. And I'll begin then by talking about brown dwarfs and talking about the clouds that we found in their atmospheres, the characteristics of the clouds, what are some of the things we've learned from the effort to understand brown dwarfs. And then I'll move on to the exoplanets, which are also cloudy, and we're finding out now also are hazy too, or are rich in photochemical hazes. So the point is to give you an overview and an appreciation that in understanding these classes of objects, you have to understand something about the clouds. So as of today, according to the online archive, there's 752 L and T-type brown dwarfs. I'll say a little bit more about the distinction between those later. Now remember, brown dwarfs are objects with masses between about 13 Jupiter masses up to about 70 Jupiter masses. They're not massive enough to fuse hydrogen to helium in their cores, so after they're formed, they cool off over time. They just fade away and radiate, getting cooler and cooler, fainter and fainter with time. The coolest brown dwarf yet known has an effective temperature of around 550 Kelvin. That's cooler than the surface of Venus. The hottest ones for the L-type brown dwarfs range up to an effective temperature of around 2400 Kelvin. The WISE mission, which is flying today, is looking for the coldest and closest and faintest brown dwarfs and may find objects with effective temperatures as low as 200 or 300 Kelvin. For exoplanets, as of Monday, there was about 460 planets of all types. With the Kepler candidates this week, there's about 312 more. About 87 of the exoplanets are transiting planets. What I'll be focusing on today, though, are the directly imaged extrasolar giant planets. Now, if you add up 460 plus the 312 Kepler planets, you start to think that maybe the number of extrasolar planets is greater than the number of brown dwarfs, which would be a first. And I sent this around just this morning to my brown dwarf colleagues, and they all said, no, the online archive's out of date, and there's several hundred more brown dwarfs yet to come. So there's still more brown dwarfs than exoplanets, but that's not going to last. Here are some examples of direct images of extrasolar planets. And this is where the field is going to be in the next 5 years. You'll be hearing a lot about these. These are objects imaged primarily by thermal emission. So looking like that Saturn 5-micron image of Saturn I opened with, looking at the heat emerging from the planet. Notably, up on the upper right are 3 planets orbiting the star HR 8799. The blob in the middle is an artifact from removing the light of the central star. But you can see the 3 planets B, C, and D, for which there's actually been seen orbital motion as these planets orbit their star. And then just last week was the announcement of Beta Pictoris B, which is shown in this composite image at the bottom with the Beta Pictoris dust disk on the left and the right, and then the planet, which was seen here several years ago and has now emerged on the right side of the star. So these are images in thermal emission. If we have launched into space small coronagraphs or large coronagraphs aimed at directly imaging planets in reflected light, we'll get images that look like these simulations. These were done by Kerry Cahoy, who was a postdoc at Ames until very recently. And here we see in 3 different colors, blue, green, and red, what an exoplanet might look like in reflected light. For example, Jupiter at 1 AU around a nearby star. But that's the future. For now, the direct imaging search is looking for the glowing heat of extrasolar planets. The next major effort to do this will be the Gemini Planet Imager, which will go on the Gemini telescope in the southern hemisphere in the next year or two, and will probably image hundreds of extrasolar planets, producing many more images like on the bottom right. These figures along the left show how the radius and the effective temperature of exoplanets varies as they cool off. These are for 2 different models of the formation of the planets. The differences aren't important here, but the red box shows the type of planets that the next generation of ground-based instruments will be imaging directly from the ground. And this range of temperatures, about 500 degrees to 2,000 degrees, overlaps the same temperature range that we find for brown dwarfs. For brown dwarfs, we're looking at balls of hydrogen and helium with an admixture of heavier elements, just like Jupiter is a large ball of hydrogen and helium with an admixture of heavier elements. Jupiter has about 3 times the heavy elements that you would expect if you had just scooped it out from inside the sun, whereas most brown dwarfs we're finding have composition close to the solar composition or within a factor of a few from that. So when you had a mixture like that, hydrogen, helium, some heavy elements, what kind of condensates? What happens? What do we get in the atmosphere? Is it just a big ball of gas? And the answer is no. This figure compares temperature profiles, so temperature soundings, you can think of it, for the Sun, an M star, an L-type brown dwarf, a T-type, and Jupiter, with a log temperature scale on the bottom. And what I've drawn in here now are these dashed lines showing the point in the atmosphere at which a solar abundance of heavy elements would condense to form these particular condensate species. For example, silicates and iron on the left, water or ammonia clouds on the left. So in an L-type brown dwarf, the temperature pressure profile, this model profile, the red profile, crosses the condensation curve for silicates, for iron, for aluminum oxide, and we'd expect clouds to be present in these atmospheres. Instead of clouds that we're familiar with, we're talking about like sand clouds or drops of liquid iron. For the cooler T-dwarfs, effective temperatures of, say, 1,000 degrees, most of their atmosphere lies in the range where there is no abundant condensate, so they have relatively clear atmospheres. But as you move even colder, you would expect to have atmospheres for which there's water clouds, and there's yet no example of that that's been discovered of an object with only water clouds. And then finally, we have Jupiter-like planets where we have a high ammonia cloud overlying a deeper water cloud. And again, for example, the GPI instrument will be looking in this spot, probing objects between the water clouds and the silicate clouds. We have, from the brown dwarfs, from those 750 brown dwarfs that are known, great spectra of these type of objects. On the top is a spectrum of a late type M star, where you can see bands of titanium oxide and iron hydride and nascent bands of water, carbon monoxide. As you imagine cooling, if that star were, if you cooled it, you turned off the internal energy source, and you cooled it down to about, say, 2,000 degrees, which is the red curve, the iron hydride, the titanium oxide bands become much weaker because these refractory compounds are condensing into clouds, and the water bands start to get deeper. As you cool it off even further, say to 900 or 1,000 degrees, we have a T-dwarf with much deeper water bands, and also the appearance now of methane. The carbon monoxide in the atmosphere has turned to methane. And then finally, in the coolest object we have, Jupiter, we have the water is gone because the water is also condensed into clouds, and we have methane and ammonia bands. With Jupiter now, the left side portion of the flux is reflected light from the sun. The right-hand portion, the longer wavelengths, is the emitted light from the interior. Astronomers like to think of objects in terms of colors. If you put on your infrared goggles, what colors would these planets have? And I'm going to show you variations of this plot repeatedly through the talk today. It's a color magnitude diagram, so brighter is up and redder in the near-infrared J minus K color is to the right. And these points represent the known L and T dwarfs at the time the figure was made. And the important trends are that the L dwarfs, the objects, remember, that have those clouds in the atmosphere, as they cool off over time, they get redder and fainter. The T-dwarfs are over on the blue side of the diagram, and there's this transition region called the LT transition that lies in between. The odd thing is that it appears, you'll notice, that the earliest T-dwarfs are actually brighter than the faintest L-dwarfs. So even though these are all just individual objects, if we imagine an evolution track going through, what this is telling us is that brown dwarfs get fainter and fainter and redder, and then something happens where they get brighter and bluer, and then they get bluer and fainter as they fade away. And so this transition between the cloudiest L dwarfs and the clear T dwarfs that are brighter and bluer is one of the key mysteries of trying to understand brown dwarf science, and that's what I'll be talking about today. And the odd thing about this is that you can go and measure, pick spectra of each of these individual objects, add up the total emitted flux, and solve for the effective temperature of these objects. And you find out that as you go to later spectral types, so these deeper water bands primarily, and also more carbon monoxide or methane in the T-dwarfs, the effective temperature, as you go to later spectral types going down in the plot, the effective temperature is falling. But notice there's this range as you transition between those cloudy L dwarfs and the clear T dwarfs, where the temperatures are all about the same, about 1,400 degrees. So the spectra is changing dramatically. The colors are changing dramatically. but the temperature is not changing at all. So how can that be that a single object could look so different over such a small temperature range? Again, that's what we want to understand. So the sort of the global goal of brown dwarf science is to use our model predictions, compare them to actual spectra of real objects, and try to understand the masses, effective temperatures, composition of the objects we're looking at. It's hard because, as I'll tell you, to try to convince you, poorly understood cloud processes are a major influence on the spectra. The opacities are also limit our ability to interpret them, and there's all kinds of atmospheric dynamical processes that are important. But what I want to talk about today and focus on is the clouds. Here's a picture of two types of clouds over the Sahara Desert, of water clouds and dust clouds. Now, of course, here the dust isn't condensing out of the atmosphere, but you can imagine in a brown dwarf atmosphere, clouds. Imagine the water clouds are iron clouds, and the dust clouds are also dust clouds. What do these things look like? How do they influence the spectra? It's a hard problem. You think about weather prediction on the Earth and understanding climate change on the Earth. Clouds are the leading source of uncertainty in predicting the details of global warming, for example. And in brown dwarfs, we have to look at conditions spanning about a factor of 5 in effective temperature, a factor of 200 in gravity, at least a factor of 10 in composition, and a factor of 10 to the fifth in the strength of what we call the eddy diffusion coefficient, which is a measure of the strength of convection in the atmosphere. So it's a huge range of phase space to try to work. And the problem of understanding these objects depends on the chemistry of the atmosphere, the microphysics of how do grains stick together, atmospheric dynamics, a whole host of issues. And underneath all of that is the chemistry. Now, this is something of an eye chart, which I'm just showing to give you a feeling for how complex the atmospheric chemistry under brown dwarf conditions can be. Here we have pressure increasing to the left on the bottom and temperature increasing down. And in this range, you can see there's a line for Jupiter on the upper left. There's a number of chemical equilibrium. The chemists like this kind of profile, this kind of plot, because the chemical equilibria curves are straight lines. For example, if you're to the right of this line, carbon in the atmosphere is present in the form of carbon monoxide. If you're to the left, it's present in the form of methane. So an object, a brown dwarf, as it cools, moves across this diagram to the left. Thanks. Again, there's another chemical equilibrium boundary between molecular nitrogen and ammonia. And down here at the bottom are the things we're focusing on today, the condensation curves for silicates, forsterite, instatite, as well as iron. If we kind of zoom in at the bottom, these are the major species that affect the spectra and the profile of the atmosphere. More graphically, we can think of, as a brown dwarf cools, moving across this panel from right to left, a hot L dwarf. You have clouds of magnesium, silicates, and iron. As you cool off, the clouds form deeper in the atmosphere. In the T dwarfs, only relatively minor species condensed. And then even cooler Jupiter, it's the same cloud decks or even deeper. And we have water and ammonia clouds up on top. So how do we deal, and what are the issues in trying to understand the effect these clouds have on the objects that we're interested in? I'm not going to speak in detail about the gory details of the cloud modeling, but rather just point out some of the things that we have to consider. One of them is the size distribution. Are all the cloud particles the same size? Is everything 1 micron? Or is there a range of sizes? In the terrestrial atmosphere, if you fly through a cloud, you find that there's sort of a bimodal distribution of particle sizes. You have lots of tiny drops that have just condensed, and then you have a second, larger population where the drops have merged together. So the large particles are important for transporting most of the mass, but you also have to understand the thinner clouds as well. What about the size and shape of the clouds? Even today, everybody that studies this problem in brown dwarf contexts uses spherical SME particles. But in reality, if you go into the lab and condense a solar mixture of materials and see what you get, you tend to get all kinds of interesting particle shapes that look like cubes or agglomerates of particles. We've also found that rainfall is important. You can't just take an atmosphere and say, well, way up in the top of the atmosphere we would have condensed certain particles and mathematically treat them as if they never leave. This is a profile here on the right of what that, we're plotting here's the pressure against the abundance of cloud particles. On the right, if you don't have any rain, you get something that looks like this dashed line with particles all the way up to the top of the atmosphere. On the other hand, if you allow these particles to fall down through the atmosphere, just like rain, you tend to get narrower, thinner clouds, as is shown by the solid line. And all of these things, the particle sizes, the size distribution, influences the opacity, how the atmosphere regulates the escape of thermal infrared radiation, which is what we're ultimately measuring. So for example, populations, if you had very tiny particles, less than, say, a tenth of a micron, produce opacity as a function of wavelength. It looks something like this, so there's lots of opacity in the optical, hardly any in the near infrared, and nothing at longer wavelengths. Whereas if you have big, gloppy 10-micron particles, they absorb all the way across the spectrum. There's a huge difference there with a relatively small difference in particle sizes. And so, again, all of these things matter. You can see why the clouds are so important in this panel, where we're plotting, imagine we're looking down into the atmosphere of the brown dwarf, just like that Saturn picture at the beginning of the talk. Here we're plotting the temperature of the air that we're looking down to, so 500 degrees at the top, 2,000 degrees at the bottom, as a function of wavelength. The dotted line is how deep we could see if there were no clouds. The solid line is given a particular calculation of what the clouds might be like, how deep we can see. And with no clouds, in some windows in the opacity, places where water doesn't absorb very well, we can look fairly deep into the atmosphere. At those regions, we're looking down almost 2,000 degrees. But if we account for the presence of clouds, the clouds limit how deep we can see. Instead, we can only look down to about, say, 1,500 degrees. Just zoom in a little bit. Here we're limited by the cloud. Here we're not limited by the cloud. If the cloud's not there, we see deep. When it is there, we don't see deep. Just like in that picture of Saturn at the beginning of the talk. If we assume we have a globally uniform cloud and just allow it to sink as the brown dwarf cools off over time, we get something that looks like this solid line that reproduces the colors. Again, this is the color magnitude diagram for the L and T dwarfs. We get the right colors, but it very, very slowly turns over to the blue. And this is not as popular with as many points, but remember, the T dwarfs are bright and blue, and just a single uniform cloud never gets back up to the bright blue region of the diagram. So clearly, we can't just have a global slab of cloud, some simple cloud that mathematically we just sink down. We have to try to compute what the cloud is doing based on the properties of the atmosphere. And there's sort of been two major schools for how we might approach this problem. Christian Helling, who's now in the UK, has a whole series of models with great and interesting complexity of what I like to call a top-down approach, where she imagines sprinkling little seed particles at the top of the atmosphere, and they fall down and evolve and grow, and then eventually evaporate as they get too deep. At Ames, I collaborated around 2000 with Andy Ackerman, who studied clouds in the terrestrial atmosphere. And I said to Andy, we need to come up with a simple one-dimensional cloud model that we can use for our one-dimensional global average models of extrasolar planets and brown dwarfs. And he told me I was insane, that in the terrestrial atmosphere, you know that there's rising parcels and there's sinking parcels, and you have to treat the problem in 3 dimensions. And if you don't treat the problem in 3 dimensions, there's no hope of making any progress. And I said, well, we know all that, but we're astronomers and we like 1D spherical worlds, so I need a one-dimensional model. So after a great deal of complaining, Andy developed a very clever approach for comparing the strength of updrafts and downdrafts and the rate of particle sedimentation in a brown dwarf atmosphere, and develop what I call our bottom-up model. And we have a tunable parameter, which we call the sedimentation efficiency. When the sedimentation efficiency is high, we don't know why. We just say, well, here the sedimentation efficiency is high. The particles are sticking together well. They're growing big. They're falling out of the atmosphere. When the sedimentation efficiency is low, they don't stick together. The particle sizes stay small, and we have a nice thick cloud. So how have we done in our job of weather prediction? I'll show you a few examples of the kinds of things we're trying to do. These are all spectra. I'm using a log scale, so we have near-infrared spectra, 1, 2, 3 microns here on the left, and then at longer wavelengths, out around 8 to 10 microns, are spectra from the Spitzer Space Telescope of brown dwarfs. And I've inserted our favorite color magnitude diagram on the upper right, just to remind us for each of these where we're looking. So here our first brown dwarf, the observed spectra is in black, and we're up there at the top right. So the earliest, hottest brown dwarfs. And this is a model which fits the best. It has an effective temperature of 2100 degrees, a certain gravity of about 1,000 meters per second squared. But the point is, this model, which includes clouds, our little tunable parameter we've set at 2, does a pretty decent job of fitting the spectra. But how do we know there's clouds there? If we take the same temperature atmosphere, but with no cloud opacity, we get the blue curve, much bigger dynamic range. And remember, the clouds have the effect of limiting the dynamic range for how deep you can see into the atmosphere. So the clouds are clearly there. There's no question. There's no single fingerprint. There's no one spectral fingerprint that we're looking at and say, oh, there must be clouds. Instead, it's the modulation of how deep we can see in the atmosphere. If we go a little bit cooler, down to 1700 degrees, again, the same dichotomy. The red curve does a pretty good job of fitting the data. It's not perfect. The blue curve, without clouds, is a very big departure. If we go even cooler, down to 1400 degrees now, again, the data is in the black, the model is in the red. Clouds are very thick, very important by now. We don't do it well when the clouds are very thick and very important. So it tells us our cloud model is as yet imperfect. But you can see it doesn't look anything at all like the cloudless model. There has to be grains in the atmosphere. But look at the temperature, 1400 degrees. We're down at the bottom right. Look at the color magnitude diagram. Now we're at the bottom right. This is an L8 type object. Let's go now to T4. So we've skipped 5 spectral types. The data is in black. The model in blue has absolutely no cloud opacity at all. There's our red dot for where we are. We've come across the color magnitude diagram. We've gotten brighter. And where have the clouds gone? 1300 degrees, just 100 Kelvin difference, dramatically different spectrum. We turn on clouds, it doesn't look anything at all like the data. You get this very squashed, very different looking profile. So again, there's this mystery of where have the clouds gone? We have our nice tunable parameter. We can change how thick the clouds are. We don't understand why we're changing it. We're changing how efficiently the clouds are growing. And here we've gotten rid of the clouds altogether. We don't understand why. What's going on? This is the great mystery. And if we plot our parameter as a function of spectral type, we find that most brown dwarfs can be pretty well explained by our knob setting about 2 to 3. And then as we get into the T-type objects, we have to turn off the clouds. It's not, there's even outliers. We're looking this week at an object that's a very unusually blue L dwarf, where we have to have very thin clouds, and we don't understand why. So what really needs to be done, and where this field has to go, we think, is to do 3D simulations of atmospheric circulation, including cloud opacity, evolving it with time, and see what it is. How can we connect the gravity, the interior flux, the composition against the cloud opacity? We've proposed 3 times to do this. And every time we've proposed to do this, we've been told, well, it's just too hard of a problem, and we haven't gotten funding. Or maybe we had a lousy proposal, I don't know. Another group, Freytag et al., though, has started to do this. These are just two-dimensional models. And their clouds are shown in orange. And they're starting to find lots of interesting discoveries that the interaction of the clouds with gravity waves produced by convection in the atmosphere is very important. So the waves propagate up, make the atmosphere turbulent, and they keep the cloud particles suspended. And so there's probably a very deep connection between what's happening in the atmosphere as it cools off, how the convection is changing, how the wave propagation is changing, and how the clouds are changing. You can see they sometimes start to get almost holes through their cloud deck, and makes you wonder, thinking back to that Saturn image, are holes important? So we've been looking at the role of holes in brown dwarf atmospheres. Again, there's Saturn, there's Jupiter there on the top right. The holes in Jupiter's clouds have been known since, I think at least the early 1970s, where they were called 5-micron hotspots. In fact, most of the flux Jupiter emits at 5 microns comes through the few little holes in the atmosphere. And the Galileo entry probe, the inner Jupiter's atmosphere, went down through one of those bright spots, one of those atypical places with no clouds. Again, our favorite diagram, populated by the T-dwarfs in blue, the L-dwarfs in red. And what we've done now is developed using a technique suggested by Colin Goldblatt, who has studied terrestrial GCM models, suggested a technique based on what people do in terrestrial GCMs for treating sub-grid scale partial cloudiness, and has allowed us for the first time to produce models in between our global cloudy models and our totally cloudless models, where we correctly compute what the object would look like if, say, it's 50% cloudy or 75% cloudy. And the interesting thing is if you follow one of these tracks across the diagram, here's at 1200 degrees, if you put in 25% holes, you jump in color from red to blue. If you put in 50% holes, you jump most of the rest of the way. And so this sort of trend in the brightening from the red to the blue might be matched just by slowly increasing the degree of partial cloudiness in the atmosphere. And so this is something we're working on now to see if this might be a rational explanation for what we see in the brown dwarfs. And also we're looking at our model predictions to see if we can predict markers that would allow us to discern the difference between, say, a brown dwarf that has 50% cloud holes versus something that has, say, suddenly thinner, globally uniform clouds. And finally, as the diagram points out, even our completely cloudless model doesn't seem to match the colors of the cloudless, famously cloudless T-dwarfs. And spectra suggests that if you have a little bit of cloudiness, you might be able to do a better job of matching the colors of the T-dwarfs. So I want to move on to the exoplanets. So I'll just conclude by saying, what have we learned from brown dwarfs? 15 years later on brown dwarfs, we know that clouds and cloud processes matter a great deal. A simple one-dimensional model identifies the important processes. Rainfall, sedimentation, in the general term, is important. We have to understand how the particles are growing and falling out of the atmosphere. Inhomogeneities in the atmosphere can be very important. But yet, the underlying physics, why L-dwarfs have a sedimentation parameter of 2 or 3, is yet to be understood at all. But certainly this is enough that we can start to pave the way to looking at the properties of exoplanets. So the directly imaged exoplanets, we have 3 around HR 8799. There's a companion to a brown dwarf, 2-mass 1207b. And if you get into the legalistic definitions of what's a planet and what's not a planet, you can worry about whether or not this is a planet. But certainly, unquestionably, a low-mass 7 or 8 Jupiter mass object. And if you plot, well, where do these objects form? Remember, these are young, brightly glowing Jupiters, temperatures 900, 1,000 degrees. Jupiter has an effective temperature of about 120 Kelvin, so much hotter than Jupiter, but about the same size as Jupiter. Where do they fall in our diagram? They fall off down here at the bottom of the L dwarfs. So they look like very cloudy but very faint L dwarf brown dwarfs. And at least one of the HR 8799 planets looks like it's starting to move across this track over to losing most of its clouds. The data on the directly imaged planets is as yet fairly spotty. We don't have great spectra yet, although people are working on it for the individual components, that we can start to study these in detail. But that'll be something that's happening in the next year or so. Certainly the Gemini planet imager will populate many more planets all through this range, and we can begin to ask the same kinds of questions and see if brown dwarfs and exoplanets behave in the same type of way when we look at their thermal emission. Looking further into the future, we also have to worry about the role of clouds and reflected light. And of course, here in the images of the solar system, as you know, the clouds play a great deal of importance. If you look in the literature of people that are trying to detect Jupiters with, say, a space-based coronagraph, they typically take Jupiter's properties and spectra and how bright it is at optical wavelengths and just assume that all Jupiters are going to look like that. And of course, that's not the case because not all Jupiters are Jupiter. We have Jupiter at 5 AU, and if we imagine taking that Jupiter and sliding it in closer to the sun, it's going to heat up, and the ammonia clouds are going to boil away, and it'll leave a global water cloud layer over the entire planet. And so a Jupiter with just pure water clouds might be much brighter and look quite a bit different than the Jupiter that we know. And then if we imagine moving Jupiter in even closer to the sun, the water clouds will evaporate, and we'd be left with a very deep Rayleigh scattering atmosphere that might look very blue. On the other hand, if you have a Jupiter at 1 AU, all that methane in the atmosphere, that can't be good, combined with ultraviolet light from the sun, and we might end up with a very Titan-like Jupiter. And so these are all the things we have to worry about and think about as we're trying to interpret the next generation of exoplanet observations. Kiri Kahoy, who did those coronagraph simulations I showed you earlier, has computed spectra for Jupiters as they might appear around other stars. At the top left, we're looking at Jupiter at 0.8 AU, so a little bit inside Earth orbit, with 3 times the abundance of heavy elements, so very much like our own Jupiter. And this just shows the color coding is a measure of the opacity as a function of wavelength at different pressures. So as you go down in pressure, deeper in the atmosphere, the opacity gets higher. And you'll see down to roughly where the plot turns from green to yellow. And so in the cloudless atmosphere, you're looking fairly deep. You see a lot of Rayleigh scattering. You can see the influence of sodium and potassium absorption and methane. As you move that Jupiter a little bit farther out to 2 AU, you get water clouds, shown there in the white, which limit, again, how deep you can see. Even cooler Jupiters at 5 or 10 AU, ammonia clouds become important. And so since these haven't been discovered yet, I don't want to spend a lot of time on them. But these are just calculations of what our Jupiter would look like in the optical wavelengths. The red Jupiter with no clouds, the warm Jupiter at 0.8 AU with no clouds looks something like this, very dark at red wavelengths. As soon as you turn on the clouds, the spectra jump up and look something like the green curve or the blue curve higher up on the plot. So clouds make a huge difference. And when the day comes, we're getting colors and spectra, directly imaged planets and reflected light, we're going to have to understand the clouds. It's interesting to ask, well, how well could we do if we were looking at our own Jupiter and if we applied these simple models to produce a prediction of what our own Jupiter would look like? An untuned model of just a Jupiter 3 times solar abundance, 5 AU is the blue curve on the right. The real Jupiter is in red. And it's not a bad comparison. It's mostly we get the methane bands right, and the depths are controlled by our simple cloud model. But look at that big difference at the blue wavelength, shortwards of about half a micron. We're totally wrong. The real Jupiter is getting fainter into the blue and UV, whereas our model Jupiter is getting brighter from Rayleigh scattering. And this difference is, again, caused by photochemistry. Let's look more closely. This is Jupiter image from Galileo looking back towards the sun at the limb. And here's the cloud deck. And you can see up above the higher atmosphere, there's this fuzziness is all caused by hazes in the atmosphere. These hazes are produced by the interaction of ultraviolet light with the methane, just like smog in Los Angeles. And if we imagine moving Jupiter even closer to the sun, to the extreme case of the hot Jupiters at 0.05 AU inside of Mercury's orbit, it's a very different situation. We've got 10,000 times higher ultraviolet flux. Not only do we have to worry about the chemistry, photochemistry of hydrogen and the carbon species, but now the water is in the atmosphere. The water clouds have boiled away, so we have water mixed all the way through the atmosphere. The ammonia clouds are boiled away. We have nitrogen, sulfur, phosphorus. And so there's many more complicated photochemical pathways. And we're only just now beginning to understand these. My colleague Kevin Zonley has been working on this problem. For example, here's the temperature of one of the hot Jupiters, HD 189733, upper atmosphere near 1,000 degrees. And what he's finding is that if you have any kind of mixing in the atmosphere, where you're mixing species up from the deeper in the interior, up high in the atmosphere, a combination of the mixing and the photochemistry can produce profiles of the chemistry that are very, very complex. The simplest kind of calculation would predict you'd have methane in this particular atmosphere, the red line, all would be more or less uniform all the way up. But when you account for the photochemistry, when you account for the disequilibrium that can happen when you're mixing the methane up, he finds you get all this other host of hydrocarbon species, HCN, C2H4, C2H2, also CO2, a very disequilibrium situation. He summarized it in this figure where what's shown in red and blue is what you would expect in chemical equilibrium, and what's shown in green is the disequilibrium species. And this is the fraction of where is the carbon. As you go to higher and more efficient mixing, as you get in these hot Jupiter atmospheres, where the atmosphere is driven by this 10,000 times the sunlight that Jupiter gets, you can see that 80-90% of the carbon is not where you expect it to be. And we're speculating that these higher order hydrocarbons are what Kevin calls soot precursors. We're making essentially photochemical smogs, maybe PAHs, things that we see in diesel exhaust. For example, big gloppy species like this. And these may very well form, again, here shows, I'll skip this slide. That in this magic region of around 1,000 degrees, 800,000 degrees, the atmospheres are not in equilibrium. They're not giving us just methane and carbon monoxide, but instead, mix in with photochemistry and the mixing from the interior, this whole host of soots. There's actually evidence for this if we look at transmission spectra. So now, remember, this is a transiting planet. The giant planet passes in front of the sun, in front of its primary star, and you can measure the size of the planet as a function of different wavelengths. If there's absorbers high in the atmosphere, the planet looks big. If there are fewer absorbers at a given wavelength, the planet looks smaller. This is the available data from the Space Telescope and Spitzer, and some ground-based data too, for HD 189733. But I just want to point out here on the left, the models for what this planet should look like are shown by the solid lines. And the actual data is shown up there in the squares where it's labeled soot. It looks like there's a population of high-altitude absorbers, very smooth, no absorption features, and these may be soots produced by the photochemical processes in the atmosphere. Yet another exoplanet, GJ436b, has also been observed in the same technique, looking at the planet as it orbits its primary star. And for this object, it's a warm Neptune. It should be plenty of methane in the atmosphere based on the estimated temperature, but yet the ratio of methane to carbon monoxide is about 10 to the 5th times too small. It's like somebody hid all the methane in Neptune. Where did it go? It's not in CO, it's not in methane, and it's probably in these hazes produced by disequilibrium processes in photochemistry in the atmosphere. This is just brand new results from the last few weeks. And so it just, again, leads us to understand that if we want to appreciate the processes in the atmospheres of not only the brown dwarfs, but also the exoplanets, we have to understand this whole host of processes of not only equilibrium condensation, the stuff that falls out of the atmosphere at a given temperature, but also the things that are produced by processes like photochemistry. So, in conclusion, the future for exoplanets and brown dwarfs is certainly cloudy. Already, clouds and hazes are important. The ground-based efforts that are definitely happening over the next few years are going to produce direct images of hundreds of exoplanets, but we can't hope to understand them unless we understand the cloud processes. JWST and HST will be looking at transiting planets, looking for hazes, looking at the chemistry of the exoplanets. Eventually, space-based coronagraphs, and there will be SOFIA, of course, space-based coronagraphs will be producing images of planets in reflected light, so we'll be able to see the white Jupiters, the blue Jupiters, the smoggy Jupiters. And just as it is now, I think, as far as exoplanets and brown dwarfs are concerned, everybody will be talking about the weather. And I'll stop there. Thank you.
So, Mark, just to clarify a point, can you just go back a couple of slides to where you were mismatching the Rayleigh?
For Jupiter?
Yeah. So, saying that the hazes are large enough particles that they're obscuring the Rayleigh scattering that you expected to see. Okay.
And they're dark hazes that absorb incident light at those short wavelengths, yeah.
So I have two kind of basic questions, maybe just things I didn't understand here. Way back at the beginning, I don't want you to have to flip back, you gave us a series of graphs of temperature versus wavelength, where you showed us how deep in the atmosphere you could look when you had clouds and when you didn't have clouds. And you gave us an example of how when there were clouds, you couldn't see as hot because you can't see as deep.
Right.
But on the rest of that same graph, the curves were flipped. And in the presence of clouds, you actually could see hotter.
So what's happening there is above, the presence of clouds tends to heat the whole atmosphere, even above the cloud decks. So at longer wavelengths, looking above the clouds, the air is hotter than it would otherwise be. And so that's why they were flipped.
Okay, so if you looked at it in terms of pressure versus wavelength, you wouldn't be seeing as deeply, but because you're looking at temperature and the temperature's hotter.
Right. So off on the right on that figure, you're looking at low pressure regardless. It's at and so the clouds are not influencing the line of sight optical depth. It's more they're changing the air temperature. So there's two different things, and I glossed over that. Yeah.
Okay. So the second question is, you were talking about, we have these color magnitude diagrams of L and T dwarfs in this transition region. You've been talking about it in terms of an evolution of a particular brown dwarf moving from one region to another. What evidence do we have that this is actually an evolutionary track and not just a set of data that's based on things that started with different metallicities or different masses or different who knows what?
You can look at very well-selected, there's samples of brown dwarfs, like all the brown dwarfs inside of 20 parsecs. And even in well-selected uniform samples, you have that same fingerprint pattern. And there's people early on said, well, maybe this is an effect of unseen binarity. So these are binaries, and we can't detect their binaries, so they look brighter. And every other explanation has not borne out based on a whole host of observations. So it really does look like this is an evolutionary process. Of course, you don't know because you can't watch one object evolve through it. But there's no objects, hot and blue objects, for example. It's just that pattern.
So you're saying basically, since they're all so close, you're expecting them to behave like stars do in clusters, where...
Well, and for example, you can look at the Pleiades, where you have a well-known age, and you, again, get that same pattern.
Okay.
So you look at different masses. So the heavier masses take longer to evolve, and they're still off there on the right. And what looks to be the lower mass objects are starting to make that turnover to the blue. So it really does look like it's a real evolution
Okay, thank you.
I was curious, Jupiter and Saturn look very different. Is that a function mostly of the temperature, differences in composition? Do we understand that?
Partly, I think. Saturn seems to have a little bit more heavy elements, more methane, more ammonia. The clouds are, Saturn's cooler, so the clouds are deeper. When the clouds are forming deeper at higher pressure, there's more stuff, so that the clouds can be thicker because you have more stuff to make cloud particles out of. And so there's more clear atmosphere up above the cloud. Saturn's farther from the sun, so the photochemistry is less important for making hazes. So there's a whole host of reasons, but why Saturn sort of has that golden hue. And those, they tend to be, those, you have to always take them with a grain of salt because they stretch the colors. But and Jupiter has, today, the reason Jupiter has that reddish tint isn't really well understood. It's probably a photochemical process of something coating the ammonia cloud particles with junk that's made by photochemistry, and the fresh particles are bright white.
There's also more detail in the cloud layer in Jupiter.
And Jupiter has more internal heat flux, so it has more energy to drive convection and drive weather. And again, the clouds are higher, so they're maybe be affected by those dynamical processes more. But as you start to really question exactly why they're different, I don't think that's perfectly well understood.
But it does seem like it's a real issue because Jupiter and Saturn are only slightly different, and yet they look incredibly different. So that must it's kind of the problem you have.
I find it frustrating that people that have come to this from sort of the astronomical side have tended to say, well, we'll be able to identify all these planets because the Jupiters are going to look like Jupiter. And we know, right, just what you said, that slight differences make a huge difference. Planets don't fit on HR diagrams the way stars do.
Do we have any idea why the red spot in Jupiter that was bright... do we understand why the red spot in Jupiter that was bright red for centuries has faded to pale pink in recent decades?
I don't know. I haven't followed that closely. But again, that's an example of the combination of the dynamical processes, the photochemistry, and who knows what are producing changes like that.
This may be a naive question, but in your discussion of the condensates and specifically CO methane ratios and nitrogen ammonia ratios, there seems to be a presumed hydrogen fugacity. Where does that come from? How do you know what the reduction potential is in these systems, and might it not? That's a complicating feature, certainly. And how would you?
Right. So you have these planets the brown dwarfs are probably 98% hydrogen and helium. So from just by starting with the assumption that of solar abundance.
Oh, solar abundance.
So you
of
start
hydrogen.
with solar abundance.
Okay.
Then we also can do the chemistry for 3 times solar abundance or 10 times solar abundance or what have you. But for every one of these models that I show, we just assume typically solar metallicity.
I see. Okay, thank you.
A short question. You talked about the bump with the small particles, the cloud particles, and then slightly bigger, and the coagulation, presumably to get it to the other bump. What was it that set the size for the small bump again? How did you choose that?
Well, so what we typically do, what Andy ended up doing, is we just use a very fat size distribution that goes from small to big. But in the Earth's atmosphere, the particles that are just condensing out of the gas onto condensation nuclei are very small. And you have a lot of these very small particles that then collide and grow into a bigger population of larger drops. And so you have the freshly condensed tiny drops and the more evolved big drops.
Okay, just very quickly, another one. You talked about a new result where a planet doesn't have CH4 because UV is causing hazes. Within the hazes, this is you would have to replace the hazes like in Titan in order to.
We're still. I mean, this is for GJ436b. This is just a few weeks old, but the data suggests that the methane abundance is like I said, 10 to the 5th orders of magnitude smaller than it should be. And so where is that carbon going to? And what we're proposing is that it's gone into these bigger hazes. It's a complicated interplay of both photochemistry and mixing. You have to have mixing from the bottom and the photochemistry from the top. And one without the other will not get rid of the carbon. We will not get rid of the methane in that way.
For the brown dwarfs where you couldn't fit clouds into the model, are you prepared to say that we're seeing the surface there, or we just don't understand enough about?
Right. So brown dwarfs are big, giant balls of hydrogen and helium, just all the way down to the center. It's fluid, so there's no solid surface.
So we just don't know what the hell's happening at the moment.
Yeah, that's right. We're working on it.
Well, if there's no further questions, Mark, we have a special SETI pin to say thanks very much in commemoration of your talk, and if you'll join me in thanking Mark.
Thank you.